Okay, good morning, everyone. Sounds like the mic is on. You can hear me in the back okay? All right. Before we get started today, does anybody have any questions over anything we discussed last time? Okay, if not, then just for a couple announcements. Remember that the data transmission homework that covers the material we finished last time will be due this time tomorrow morning. So please, if you've got questions, post them on Blackboard. I know I have office hours later this afternoon. I believe David also has office hours later today. So please come get your questions answered. Remember, that's due tomorrow morning. Shortly after it's due, I will post the solutions for you to look at. Remember that we then have our quiz on that unit Wednesday at the end of class. So again, look at those solutions and post if you've got any questions or bring them to class Wednesday morning. Also, just as a reminder, sort of looking out a little bit more on the horizon, all the way into the future, exactly 3 weeks, first draft of the term paper is due. I know it sounded like at the beginning, like, oh, this is at the end of the semester and it's a long way away. Well, we're getting close. So just keep working on it, keep doing your research into your topic, work on it, let us know if you have any questions, but just keep that deadline in mind that it is actually approaching. Okay? So I guess, any questions on that before we jump into our new unit? Okay, so then we're going to start our third and final unit on this sort of digital devices super unit, where we're talking about whether it's computers or smartphones or tablets or whatever the case may be. We started off looking at sort of how do these devices work in a general sense, and how do they store and process information. And that was sort of our first unit. Then we had the one that we just finished, talking about how do devices send data to and from each other, and how can we think about errors and ways to deal with errors that are going to creep up during communication. And so sort of the quick summary of last time is we asked questions like, how many errors might we expect during transmission when we're sending some number of bits between two devices? And are there any tricks we can use to help detect and or correct any errors? And hopefully you know now the answer to the bottom question is yes. Okay? What we ignored during that, we hinted at it a little bit, so maybe ignored is too strong of a word, but we didn't really take into account this idea of data security. We were just looking at, does the message, whatever those bits are, get relayed correctly? And we never really stopped to think, well, but is it secure? So we can get the information there, but how do we prevent unintended parties from accessing that information while en route? You know, is this something that we necessarily want to care about? Is data security important? Okay, so I've got a couple applications here. Those of you that have set up online banking, do you want data security? When you're communicating with your bank online, do you want, you know, someone to be able to intercept your bank account numbers and your passwords and, I don't know, your net worth? Not really. I'm guessing some of you have started to the point now where you've had to actually do IRS e-filing, usually in March or April, although perchance in May or June if you're willing to pay a penalty. Anybody had to deal with that and file a tax return? Okay, a couple hands have gone up. Do you want that information insecure? When you're sending it from your computer to the IRS, do you want anyone on the internet being able to see that information? Not really. What about your emails? Do you want your email messages to be secure, such that the only person who sees the message is the person you sent it to? Maybe not always. Probably some messages don't really matter. But do you send messages where maybe you want privacy? Yep. Can you think of other types of applications? When we're sending data now, when might privacy and data security be an important concern? Can you think of other applications? These are a few that I thought of. Any ideas? Yep.
I guess maybe like the storage in our phone. Some people.
Okay, so you store things in your phone, and maybe you want to keep that secure. We'll actually come back to that point with a contextual example here in a few slides. Absolutely. Yeah. Okay, so military secrets. So these have to get communicated. There was a big deal made about this last year with someone's emails, one of that person being a presidential candidate. And did we care about security in that case? More or less. Yep. So maybe there are some things from a governmental perspective that we want to keep secret, but we still have to communicate them to different people who need to know that information. That's one of those government phrases, need to know. I never had a clearance and never needed to know, and I was perfectly happy with that. Other ideas of why data security, where data security might be important? Okay. So how does data security work? Well, the big thing that it encompasses is this idea called cryptography, which I'm guessing most all of you have heard before. And to take the definition from dictionary.com, it's the science or study of the techniques of secret writing, especially code and cipher systems, methods, and the like. So again, secret writing. How do we take our message and encrypt it in some way such that it's not obvious to anyone who sees the message what it is that we're trying to say? So historically, what are different ways that we've gone about doing cryptography? Do you have any ideas sort of historically? How would we make messages secure? Any thoughts? Or is it too early on Monday morning and we're all still a little sleepy?
So if you had a message to send, like in a battle or like in a war context, they would use like a secret code, and both sides would have the code, but on transit, you wouldn't have the actual message.
Okay, so the idea was maybe in like wartime or something, going back to sort of military, both sides, so you'd have, here's the commander in one place and here are the troops in another theater of the war. And maybe they would have communicated beforehand and said, here's how we're going to encrypt messages. So then now they're at the different places. General sends an order. It's encrypted while it's in transit. So if it gets intercepted, no one can understand it. And then it finally gets to the front line of the battlefield. They get the message. They decrypt it, and they can interpret the orders and then do or not do whatever they were told to do or not do. Okay, that's certainly one possibility. Anybody have other ideas of how historically we've encrypted messages or used cryptography? Yep.
Well, you could, like, for example, if someone, like, who can intercept the message doesn't know a specific language, you could use a specific language.
Okay, so that's a great example. So let's say you're going to send the message and you're going to put it in a language that may not be known to everyone. And so even though you're not necessarily encrypting it in a very complicated way, it still makes it hard for an interceptor or an eavesdropper to understand. Do you know an application when this was used? There's one in particular I have in mind. Okay, so we talked about in the last lecture, in the last unit, going back to World War II in cryptography, and we saw that the Axis powers had a machine that allowed cryptography to keep their messages secure as they were communicating around. We saw a picture of it. It was called the Enigma machine. Okay, so that was also one way historically that we've done cryptography. Does anybody know what the Allied powers used? So Axis powers had the Enigma machine. What did the Allies use? It was Native Americans. And so they basically took a lot of their messages, converted them or translated them into, it was usually Navajo, I believe, and they were just communicating them in Native American languages, because these languages developing independently sort of on North America were so distinct from anything that you would see in Asia or Europe that the Axis powers just didn't really have access to anyone that spoke the language, and that made it in many ways just as secure as the complicated machinery that the Axis powers were using. So these are all different ways historically. Does anybody have other ideas of what we've done to make messages and data transmission secure? So I'm proud to say we've sort of hit all of the ones I had in mind. And so there's our picture of the Enigma machine again. And as we said up above, a lot of times what we'll end up using are called ciphers. So let's dig into that a little bit. So what is a cipher? Basically, it's just an algorithm used to encrypt and decrypt data. And there are different types of ciphers that have been used throughout history, one of which, being fairly straightforward, this is not a very good one to use by modern standards, but it has been used quite successfully in past times, is to replace each letter of your message by another letter. And so basically it makes the original message seemingly unreadable. Okay? So if we were to take an English sentence and replace all of the E's by X's and all of the X's by A's, and so on and so forth, is this going to produce a string that looks even remotely intelligible? No. Turns out, from a computational perspective, this is a pretty easy cipher to crack. But if you're just looking and working with human beings, I don't know, if anybody's into logic puzzles or if you've gotten one of those like penny press logic puzzle magazines at the airport, this is sort of a common thing that'll appear in those. Okay, and for instance, so we've already seen a substitution cipher. We didn't think of it as a cipher, and it wasn't really used to encrypt data, but we've still seen one. Does anybody want to take a guess what that might be? It's the ASCII table. So when we were going back to our data storage unit, we took, here are the letters that we have, and we associated a number with each one of them. We substituted for each of these symbols, here's a number. And so in the homework assignment, I think I gave you, here are a bunch of numbers, and you had to convert them back to ASCII. Before you actually went through and decrypted that, was it obvious to you that that message was, this is really tedious? No. Okay, so could you think of that message as having been encrypted, and you were decrypting it? Sure. That wasn't really the context. That's not really why we have the ASCII table, but you can regard it in that way. Okay? There are several other types of ciphers. Just real quick, there's also this idea of a shift cipher. Shift cipher is a type of substitution cipher, but in a specific way, where rather than just sort of randomly mapping the alphabet, we can take maybe D here and route it down into an A, E into B, F into C. So we're still substituting. All the D's here get replaced by A's. All the E's get replaced by B's. But the idea that whatever order the letters were in originally, they're still in that order at the end. So we're basically just sort of shifting the alphabet some number of digits over. Okay? And there are plenty of other types of ciphers. If you're curious, the Wikipedia page actually has quite a bit of information on it. You can see plenty of examples of cryptography. TV shows, movies, and books talk about it, maybe not frequently depending on what type of TV show or book you're looking for, but it's usually in the guise of cybersecurity. So again, we've talked about some of these cop procedurals like the Law and Order and the CSI and all that. Do you ever see cryptography come up? They're talking about, oh, we have this message, we've got to crack it, and oh, look, hey, we got it by the end of the episode, yay us. Everybody's seen that happen before? Okay, so there's that. Sort of from a more comical standpoint, did anybody watch the show Futurama? Okay, there's a handful of hands go up. Maybe you're too young for this. Anyway, throughout the show, there were several alien languages that would get featured, and so they had these weird symbols on top here. There were two in particular that the writers came up with. One of them just happened to be a straight-up substitution cipher. And so if you were to take the various messages that you would see through the show, you could match up different symbols. So this circle with sort of the four little arms coming off at the northwest and the southeast and so on directions corresponded to the letter D. And they were just using a straight-up substitution. So it looked like this weird alien language. It was just substituted English. But you can see plenty of other examples as well. And then, so for other ideas, are there any legal or ethical challenges dealing with data security? Or have we answered all of these things to our greatest content? Okay, so one particular sort of thorny issue, if you remember about a year and a half ago, there was this San Bernardino iPhone case. Does anybody remember this or vaguely remember hearing about this? Does anybody know what it was about? Does anybody remember?
This is about like a gang, something going on with the gang, and the guy gets arrested. They want to open up his phone to see if he was affiliated.
So.
Whether Apple would be able to open up the phone or not.
Okay, so a lot of that was on the right track. It wasn't quite right on the instant, so it had nothing to do with the gang. The San Bernardino iPhone, there was terrorism that was conducted in San Bernardino. They arrested the guy, and unfortunately, in the process of apprehending him, he was killed. Okay, and so now they were able to get his phone off him, and they're trying to determine, was this sort of a lone wolf attack, or was he part of a bigger cell going on to try to then determine, was this sort of the end of the threat, or is there a new chapter unfolding that we need to be aware of? And the issue is, okay, when you have your iPhone, or if you've got an Android or some other type of phone, does the phone manufacturer provide tools for you to secure your phone? Do you need a password to unlock it if you've set it up the right way? If you don't need a password to unlock your phone, you should go fix that after class. Okay, you should lock your phone. It's a really good idea. Okay, and so the issue, though, is now the government has this phone, the guy is dead, and they need to get access to the data on his phone. And so are they able to just simply bypass the security measures? No.
Wasn't that like the big problem was that they were asking Apple, can you help us get into the phone? And for Apple to get into code. I think that was like the
Yes.
that they had to rewrite some code, and that would open up other phones to do.
Right. So the big issue here comes down. There are a couple issues here. So basically, what the big case was the government then petitioned Apple because the government says we can't get into the phone. It's locked. And so they went to petition Apple to say, we need to get into this phone, and well, you made the phone, and you wrote the software, so you can write software that will get us into the phone. Okay, so the bigger issue here, it gets a little bit more, it gets a little crazier. Apple put in a new security feature at the time with the latest iPhone update when this happened, that after so many incorrect attempts on the password, what do you think would happen? It wipes your hard drive as sort of the data security to truly prevent unauthorized people from getting access. Well, so the government was a little bit clumsy when they first got the phone, and they put in one guess short of the maximum number of attempts. So normally the way the government, the NSA, again, to my knowledge, I've never had a security clearance, basically uses brute force methods to crack things. So when they want to intercept and read your email, or all these other messages, they're going through and they're just brute force trying every password they can possibly think of until one of them works. Okay? Does that sound very efficient? No, but this is why the NSA has really big supercomputers. Okay? And so the issue is that strategy no longer works here because they had maybe 10 attempts to get into the phone. Are there more than 10 possible passwords? Yes, hopefully there's probably like tens of thousands, if not millions of possible passwords. Well, crap. Okay, so the government realizes this too late, and now we're at the point where they can't make any more guesses. They have to get the next one right, or the hard drive's going to be wiped. So they go to Apple and say, well, can you write more code for this? And Apple sort of says, well, I mean, in principle, we can. But the issue is they've spent millions, if not billions of dollars working on software to make these phones as secure as possible. So then, at the behest of the government, for this one case, do they want to go and undo all of that work? Not really. More than that, once they create this workaround, which would have required completely changing or modifying the phone's operating system, is that patch, is that workaround going to be restricted to this one phone? Or could it potentially be hijacked and given to other iPhones? Could the government start abusing it and say, not just applying for this one, even if it doesn't get out to the general public and to hackers and things like that, but the government now has this tool that can unlock any iPhone? Is that something we necessarily want? No. And so this was some of the controversy that went on a year ago, is coming back down to these ideas of what is privacy in the digital age? Who enforces it? Who's responsible for it? Maybe from a more general perspective, can we even expect privacy? I don't have the answers to these questions. Some of you, I'm sure, are interested in law school and legal things, and maybe this is what you're going to make your career solving and figuring out, because this is something we as a society have not figured out how to deal with yet. So there are lots of interesting and thorny questions open here. Anybody have any other ideas or thoughts on sort of legal or ethical issues of data security? Anyway, if you're interested in some more information on the San Bernardino case, there's a really nice article from Wired Magazine. I've got the link there for you. You can click on it and read at your leisure. And so we can now start to transition into what are some of the challenges now modern day with cryptography. So why are those substitution ciphers that we saw a moment ago, why are those maybe not great? Well, I said they're easy to crack. What does that mean? They're not that secure. You take a good supercomputer, like something we suppose the NSA has, and they can probably crack that thing, give it a few seconds. Okay. So if we really want good security, that's probably not great. This is going to be a great cipher. If you're going to send a letter to your pen pal in Brazil, you're going to put it in the post office, and you don't want anyone to read it, because is anybody probably going to take the time to take that message, digitize it, put it through a computer, and interpret that you said, hi? Who knows? Maybe they would. Okay. But so to make cryptography work, we have to use these things called cryptosystems, which again are basically they're methods for cryptography. The cipher is a part of them. So they're algorithms used to encrypt and decrypt data, but also how do we actually transmit the data then as well, and all of the considerations that have to be made in that part. And so the biggest thing that we have to do in the beginning when starting to think about cryptography is that the sender and the receiver have to agree on the cryptosystem, which is to say they have to agree on the cipher that's going to be used. Why do you think we need that? Why do the sender and the receiver have to agree on the cipher? So that they can both get the message. If I were to take a message that I have specially for you, and I encrypt it, but I don't tell you how to decrypt it, does it do you any good when you get it? No. Not unless you've got a really good NSA supercomputer. I'm going to guess most of you don't. Okay? And so we would have to agree beforehand to say, here's the algorithm we're going to use so that when I send you the encrypted message, you know how to decrypt it and read what I wanted to send you. Okay? So now we get to the question then, how do the sender and receiver agree on a cryptosystem? How do they agree on a cipher? Any thoughts? Okay, so they have to communicate and develop one together. So that's sort of what we got here on the first bullet. So they could send some messages to each other to communicate, to say, hey, here's how we're going to communicate. But now here's the rub. What if those messages are intercepted? So the whole idea here is we're no longer thinking about sort of lossy versus lossless channels. We're now thinking about secure versus insecure channels. And so does it do you any good sending information on how to communicate securely through an insecure channel? No, because you have to make the assumption someone intercepted that message, and if they intercepted it, would they now know what cipher you're using, and would they know how to intercept and decrypt any sensitive information you were to send? Conceivably, yes. And so this actually turns out to be the hardest part about doing cryptography, is just getting a sender and receiver to agree. The actual cryptography part, the actual encryption and decryption, is not that hard. It might be quite tedious in certain cases, but conceptually it's not that bad. And so our driving questions as we work through this unit is going to just sort of ask, how do modern cryptosystems work? What are the tools that go into them? And fundamentally what this really boils down to is, how do we get the sender and receiver to agree on a cryptosystem and then use it to securely transfer that information? And so the answer to that question, at least in sort of a one-slide summary, is that we're going to use this thing called public key cryptography. Has anybody heard of this before? Or you've heard about public keys and private keys? Oh, good. Then I got lots of stuff to tell you all in the next day or two. Okay. So as we've said, the big challenge is getting everyone to agree, because they have to use the same cipher, the complementary encryption and decryption routines, to get the messages, otherwise they're not useful. If we didn't agree on the same decryption and encryption routines, maybe our method is too secure, because I encrypt the message, you get it, and can't do anything with it. And so, sort of, again, historically thinking back, how might we get people to agree on the cipher on the cryptosystem? Well, we've already said the idea, well, maybe we could send messages, but there's the issue of, well, what if those messages are intercepted? Okay, well, that's not great. And so maybe what we did originally, as was mentioned a little while ago, was we take the two parties, they meet personally at some point prior to the exchange of secure information, and they agree in person without having to send messages over an insecure channel. If we're both in a room and I can just tell you here's what it is, and we'll assume there are no bugs in the room and no one overheard it, is that a secure communication? Sure. Why does that not necessarily work so well today? If I want to send you an email and I want to do it securely, do I ever have had to meet with you? Has my computer ever had to be directly connected to your computer? No? So is this really a practical situation in the modern day? No, not really. Okay, so maybe then something modern day is maybe we spend a whole lot of money and we develop actually a secure transmission channel. And we can use that at the beginning, so you have a secure phone, and I have a secure phone, and I can tell you the cipher I'm using is add4. Okay, that's a really bad cipher. But in principle, could I communicate that to you? You now know the cipher, and when I start sending you later encrypted information over the insecure channel, can you interpret what's going on? Yeah. Okay. Why might we want sort of these two layers then? We've got this secure channel and this insecure channel. Why would we bother with the insecure channel if we had that secure one? If I had the secure phone, why would I bother emailing you something over the internet? Maybe it's really expensive. And so, I don't know, maybe every time we have to send a message over the secure phone, it costs $1 million. Maybe we don't mind paying the $1 million to say, let's set up the secure thing, but then every time I need to tell you the position of, I don't know, whatever troop movement is somewhere, do we want to spend $1 million every time that changes? No, just send it through the internet. It still costs money. We don't think about it, but it's probably not $1 million. Okay. And so the couple problems here are, number one, do we ever have truly a secure channel? I don't know, maybe again if we're a government official, and I'm sure the US government has secure phones. You see them on TV shows. I'm not entirely sure how accurate that is, but we'll run with it. But barring that, do average people have secure phones? Not really. So for mass production, is this really a viable option? No. What we have are just sort of these insecure devices which only have insecure channels. There's no way for us to necessarily meet privately beforehand to agree on what the cipher is going to be. So how do we make this work? And the big idea is we can use this thing called public key cryptography. And this is what we're going to be working towards over the next it might spill into lecture next Monday as well, is developing this. And so one of the key things that we're going to need to discuss to start to build up towards public key cryptography is this idea of what's called Diffie-Hellman exchange. So Diffie-Hellman exchange is named after two either mathematicians or computer scientists, and their names are probably Diffie and Hellman. This is a picture of them, and you can tell they did their work back in the 1970s. At least I think it's pretty obvious from the picture that something was going on in the 70s. This is really cool stuff. And so it turns out to actually not be that complicated. We're going to talk about it in full detail as this unit progresses. I just wanted to point out, though, that last year, the work that they did, again, back in the 70s, was awarded the Turing Award. So the 2016 Turing Award, which is the equivalent of the Nobel Prize for computer science. So this really is top-level work, and this is what has enabled all of modern secure communication and cryptography to move forward. Okay. So if you're curious a little bit more about the Turing Award, there's a link to the New York Times here, and I got the picture from that site as well. But we can talk about this. Again, it does not really require that complicated of math to see and understand how this works. But before we jump into the math, perhaps we should discuss a little bit more of what's going on. So for some notation and some lingo, when we start thinking about Diffie-Hellman exchange or cryptography more general, usually the parties that are communicating, and I don't know why this was chosen, but this seems to be what everyone does, is we're going to have Bob and Alice. Bob and Alice are communicating. So if you go read any textbooks on cryptography or you go look at any research articles, you're going to see Bob and Alice. Dropping down to number 3, we have an eavesdropper. What is her name going to be? Eve, because it's eavesdropper, haha. Okay, so basically, the way Diffie-Hellman exchange works is that these two parties to communicate, they're going to need to agree on a key, and that key is typically denoted K for key. And this one number, this key value, is what's going to enable this secure transmission to occur on top of this insecure channel. Okay? And what this basically means is that K, that key, specifies the cipher. This is going to be the key part, pun intended, of getting what is that cipher and how do we actually do the encryption and decryption per se. And so the main idea is that each party, both Bob and Alice, are going to secretly generate part of the key. Emphasis on the word part. Okay? What they're each going to do then is derive something from that part that they generate. Okay? So it's not the actual secret part that they've got, but something derived from it, which they will share. And that's what they're going to call a public key. It's public because they're willing to share it. Okay? They will then trade these public parts. So Bob will send his public part to Alice, Alice will send her public part to Bob, and using the other person's public part and the part of the key that they generated, they're able to agree on the same value of K, the same total key. With the idea that if an eavesdropper, if Eve was listening in on their communication, she's only ever going to see those public parts that are exchanged. And from those public parts alone, it is very hard to determine what was the secret. Okay? Conceptually, that's all that's going on. There's a good amount of math behind it, not complicated math. Tedious, absolutely. Complicated, no. But we'll get to that a little bit later. And so I think the best way to sort of see Diffie-Hellman exchange is with this motivating analogy that I originally got from Wikipedia, but it's really surprisingly accurate, okay? And so let's think of, instead of exchanging numbers and digital information, we're going to exchange paint colors. I know this sounds like your 4-year-old little brother would, something he would do, okay? And so you can see here up on the top, we've got sort of this whole pipeline here. We'll talk about this in part. But we've got Bob and Alice, and they want to communicate. And so the way Diffie-Hellman exchange works, as we just said, is they're both going to agree on some common color. Okay? So they have to start with something. This is not a secret. If Eve happens to know this common color, so this yellow that we've got up here on the top, Eve can't do anything with that information alone. Okay? So we can exchange that. That can go over an insecure network. That's fine. Once Bob and Alice have agreed on this common color, or this common paint as the picture is pointing out, they each choose a secret color. Again, this is that, what is that information they're each going to choose, and they're going to keep secret. Okay? And so Alice here chooses, can we call that orange? Burnt orange, maybe? Bob chooses teal. Okay, maybe more like, yeah, we'll go with teal. Okay, and so they choose those as their secret colors. We can see these right here. And so what they now do is, using this common color that they agreed on and their secret color, they can mix those two together and form these two new colors. So the yellow plus that orange might make sort of this peach-colored bin over here. And when Bob mixes that yellow common color with the teal, we get this sky blue. Okay, so now, are those two colors, are the peach and the sky blue actually the secret colors that Bob and Alice chose? No, but they're derived from them. We had to use that secret color to get the peach and the sky blue. So now, Bob and Alice trade the peach and sky blue with each other. And that can go over the insecure network just fine. Okay? And so what now happens is, Alice receives the sky blue from Bob, Bob receives the peach from Alice, and now they mix in their own secret colors. So Alice now adds the orange to the sky blue to get turd brown. Okay. Bob then adds his teal to peach, which also gives us turd brown. And so have Bob and Alice agreed now on that common secret? Yeah, they both have, at the end of the day, turd brown. Okay. So the key now is, pun intended, what's the possible information that Eve can intercept as they're doing this communication? Well, she might be able to guess that the common paint color up here at the top was yellow, and she can get that Alice's shared information was peach, and Bob's shared information was sky blue. Is that enough information for her to determine, I guess the end goal, what is the secret? What is this final color, and was it brown? Or more specifically, what were Bob and Alice's secret colors? Could Eve determine that Alice had orange and Bob had teal? Yep.
Are we assuming that only one color would resolve into like that lighter blue? Because if we are, then wouldn't she be able to figure out which was the secret?
Okay, so the question is, are we assuming that only one color can resolve into this sky blue here? I don't think we can necessarily make that assumption. It could be true. But you did arrive exactly on the main point. So what we're relying on in this exchange is that it is very, 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 well, it's not actually text, so I can't highlight it, but we've got the word here, expensive, to separate out paint colors. So Eve intercepts the sky blue and the peach. It is incredibly expensive for her to separate that into either the orange and the yellow or the teal and the yellow. Can she do it? Probably. Given enough time, given enough money, and given a really good paint separator. I'm not sure that's really a thing, but okay. Bear with me for the analogy. Is it possible that Eve could do it? Yes, but this might take, I don't know, millions of dollars or weeks or years. And if you're sending a simple email with saying, yes, let's meet at the movie at 5 o'clock tonight, is that information going to do Eve any good in 10 years? Probably not. And so is Eve necessarily willing to invest the resources needed to determine that secret 10 years from now? Probably not. And so that there is the underlying idea of how these cryptography systems work. It's not that Eve doesn't know how to crack the message? She does. It turns out the algorithms that are used all over the place to do secure communication are not that complicated and well known and well published. The problem is they're expensive to crack. This is why the NSA has huge supercomputers. They know what they need to do. It's just going to take, I don't know, days, months, years to do it. And so they throw a lot of computing resources at it, saying, well, we got to spend a lot of power, but if we can still get it in a day, maybe we can thwart that terrorist attack, or realize we can get John Podesta's recipe for, what was it, risotto. Anyone following last year's election, you could look that up. It's a pretty good recipe, actually. I tried it. John Podesta was Hillary Clinton's campaign manager. That was one of the things in her emails that came out, was his risotto recipe. Anyway, but that there is basically the entire idea, at least in this conceptual way, using paint colors, of how Diffie-Hellman exchange works. Again, both parties choose part of the key. Alice's part was the orange color, Bob's part was the teal color. They derive something from that, the teal and the sky blue, share that, and continue on. But at the end of the day, both Bob and Alice are able to agree on that common secret without having to share that private information that they want to keep private. Okay? So now, what we need to do before we actually dig into what is that key K and how do the actual cryptographic systems work, we need to step back and discuss a few math concepts, which will probably occupy the rest of the lecture today, if not part of the lecture on Wednesday as well. And in particular, we're going to need a couple things. We're going to need to look at with this thing called modular arithmetic, and we're going to need some elements of number theory. Okay? And we'll work through these in turn. So modular arithmetic, again, taking the definition from Wikipedia, is a system of arithmetic for integers where numbers wrap around upon reaching a certain value, and we call that value the modulus, thus how we get modular arithmetic. If you're looking for supplemental resources, there's a whole bunch of nice ones. Wikipedia actually has a really nice discussion of this. The Khan Academy has slides. There's an article linked there for fun with modular arithmetic. I know you probably think that's an oxymoron. And there's some other slides there that I based a lot of what we're going to talk about off of. But please give those a look if you have questions. But before we get in, so we have this idea of modular arithmetic, where we can do arithmetic, addition, subtraction, multiplication, whatever, but our results wrap around to be smaller than some modulus. It's a very well-known example. Anybody want to take a guess what that might be? You probably studied it in like first or second grade for modular arithmetic. Okay, so don't everybody look at once, but there's something in the center of the room at the back. It's a clock. We can do clock math. Anybody remember doing that and thinking in first grade, this is really stupid? Okay, this is modular arithmetic. So the idea, okay, so I overshot. It's only 9:05. I know, you wish it was 9:30. The time is 9:30. What time will it be in 50 minutes? No, seriously, what time will it be in 50 minutes if it's 9:30? It's going to be 10:20. Okay. And at 10:20 a.m. What time will it be in 12 hours? 9:30 p.m. Okay, so when we added the 50 minutes, you know, we know that that minute part has to be between 0 and 59. We know that our hours part has to be between 1 and 12. Okay, we're going to use the American system and not the European 0 to 23. You can use either one, it doesn't matter. Actually, the European system works better for modular arithmetic in principle than the American, but que sera. Okay, but this is something that we're all very familiar with. But this is just modular arithmetic. Take your minutes, add it, and take whatever comes out and put it back between 0 and 59. And if we need to fudge the hours part to make that work, so be it. Okay, same thing with the hours. If we add, I don't know, 3 hours to 9:30, we would get 12:30. We added 4 hours, we wrap back around to 1:30. Okay? And so basically, as we've seen, we can start to develop modular arithmetic, which is to say we'll get to addition, multiplication, all of that, with the caveat that whatever that final result is going to be between the values 0 and n minus 1, where n is the modulus. For minutes, what was our modulus? 60. There's 60 minutes in an hour. For hours, what was our modulus? And we need to modify the statement just a little bit, but it's nominally 12. Because once we go past 12, we wrap back around to 1, count back up to 12, wrap back around to 1, count up to 12, wrap back around to 1, and so on and so forth. And so the way that we can write this is instead of just having whatever our result is m, we're going to write it as this notation m and then in parentheses mod n, which is to say take whatever our number m was, the result of whatever addition, multiplication, whatever we needed to do, and wrap it back around so that it has to be between 0 and n minus 1. Again, n being what's called the modulus. And there are basically two ways to go about calculating this. So whatever our value m is, and assume n will be given. Okay, when we're working with modular arithmetic, we're going to assume the modulus is known. What we can do is sort of two things. We can add or subtract multiples of n, of our modulus, to our number m, until the number that results is between 0 and n minus 1. That's sort of a long way to do it, but it will work just fine. The easier way, in most cases, is to use long division and actually do m divided by n and take the remainder. Okay? And we'll work through some examples of this here in a minute. But let's think back to our clock math first to sort of see how this works. So we had the example that 50 minutes past 9:30. Well, maybe if we were just to add the minutes, we would get 9:80. If I were to tell you the time is 9:80, you're going to look at me like I'd gone round the bend more than usual. Right? Okay. Because what we know is that, well, that minutes digit shouldn't be 80. That's weird. That's unconventional. We know it should be between 0 and 59. Well, if we look, if we actually were to do the long division of 80 divided by 60, how many 60s are there in 80? There's 1. And what's left over? 20. So we could say 80 divided by 60 is 1 remainder 20, as we've got sort of right here. So we know when we do this clock math, the resulting minute is 20, because that's what's left over, and we add the 1 into the hours digit. Think about it just sort of carrying the 1 over to the hours. And 9 plus 1 was 10. Is 10 a valid digit for the hours? Yes, it's between 1 and 12. And so we write that the time, the final answer then was 10:20, noting again that 80 modulo 60, or 80 mod 60, is just that remainder is equal to 20. Okay, so that's sort of one simple example from clock math. And we can do a few more examples. So maybe take a moment and think about what 6 mod 7 might be, or 17 mod 4. And we'll talk about these through maybe in 30 seconds or something. All right, anybody have a guess? What's 6 mod 7? Anybody have an idea? It's just 6. Okay, so we can ask ourselves, is 6 between 0 and the modulus minus 1? Yep, because modulus minus 1, the modulus here is 7. Is 6 between 0 and 6? Yep, we're done. Other way of seeing that, how many 7s are there in 6? There aren't any, so the remainder is 6, which would be our modulus. Okay? So likewise then for number 2, how many 4s are there in 17? There are 4. What's the remainder? 1. So what's 17 mod 4? Just going to be 1. Okay? So now that we sort of know how to find these, and those were some pretty simple examples using small numbers. We'll certainly see bigger numbers as this unit progresses onward. We can start to define and look at addition, subtraction, multiplication in modular arithmetic, just like we could think about addition, subtraction, multiplication normally. And it turns out that addition and subtraction are actually pretty straightforward. So suppose we wanted to take two integers, a plus b, and we want their sum modulo n, or mod n. Okay? One way we could calculate that is we could actually just calculate the sum a plus b and then determine what's it modulo n. Look at how many n's are there in a plus b, find the remainder. Another way that we could do this, if we were so inclined, is we could actually calculate a mod n, which will now give us something between 0 and n minus 1 inclusive. We could calculate b mod n, again, something between 0 and n minus 1 inclusive, add those together, and then take that mod n. So now we've had to calculate 3 moduli instead of just 1. What's the caveat of doing it this way? Anybody have a guess? Are we ever going to get a really large number if we do a mod n plus b mod n mod n? No, everything we're going to work with is basically going to be between 0 and n minus 1. So we keep our numbers small, because maybe, I don't know, maybe a is 100 digits long, and maybe b is 100 digits long. Okay? And it turns out we can see that subtraction works the same way. If we want to just take a minus b mod n, we can take a mod n minus b mod n, take that whole thing, mod n, and we can do the exact same thing for products. And that's the one that's going to be really useful as we move on through this unit, is if we wanted to have now just a times b mod n, calculate a mod n, multiply that times b mod n, and then take the modulo n one more time. So we can actually verify this a little bit using 3 values. So let's suppose a is 11, b is 15, and we're going to take all this modulo 8. Okay? So let's flip over here. I'll put those numbers back on the slide momentarily. And so what we had? We had a was equal to 11. B was equal to, what do we have, 15? And n was equal to 8. So what we're looking at trying to calculate now is a plus b mod n. Okay, so what's a plus b? Let's just do this the direct way. We can get 11 plus 15 mod 8. Okay, I know this is a really silly example, but you can do this with larger numbers and it works just fine. And so 11 plus 15 is just 26. Take that mod 8. Okay, so we ask ourselves, how many 8s are there in 26? There are 3. 3 times 8 is 24, so what's the remainder? We have 2. Okay, so that really wasn't that painful. Fine. Let's now look, and what we saw was we could also write this sum modulo n as a mod n plus b mod n. That's sum mod n. And so let's look at that and verify that we get the same thing. So if we wanted a mod n, well, this is just going to be 11 mod 8. Okay, how many 8s are there in 11? There's 1, and the remainder is 3. We can get b mod n. Again, b is 15. Take our mod 8. How many 8s are there in 15? 1, and what's our remainder? 7. And so if we now wanted to look at a mod n plus b mod n mod n, this is now just going to be, well, a mod n was just 3. B mod n was just 7. We're going to take this all mod 8. Well, 3 plus 7 is 10. How many 8s are there in 10? 1, and what's the remainder? 2. Okay, so did it matter which way we went? Nope, got the same result. In this case, the direct way was probably simpler, but if you had really large numbers, using this mod formula down on the bottom half might be the easier way to go.
How do we determine what operation you can use in those conditions?
So how would we know what operation? That'll be specified in some way. So this isn't just sort of like, here's the random rule. You're going to know. We're not going to see a lot of the addition and subtraction in application, but the multiplication one is going to be very important when we start coming back to Diffie-Hellman exchange and all that next time. Okay? Any questions on this? If you wanted to, you can also go through and verify subtraction works. You can verify multiplication works. Or you can just take my word for it. That's up to you as well. Yep.
So like, just out of curiosity, if we did a subtraction, 11 minus 15 would be a negative.
Yep.
So we just figure out how many.
So negative numbers get a little bit fun. So what you would end up doing is, again, just do the long division. So find out how many 8s are there. In that case, it would be a -4. And the answer is there's -1. Because you got to go below. And then what's the remainder? So if you had -1 8 is -8. So what's your remainder to get back up to -4? 4. That's what I'll give to you. We're not going to do negative numbers in here, but the idea works just fine. Yep. Okay. So we can do that. And if you're curious, when we introduced last time, remember when we were talking about our error detecting and error correcting codes, we introduced this idea of binary addition. It turns out that was just addition modulus 2. Okay? Because we could always take it if we had the 1 and the 1 and added 1 plus 1, we would nominally get 2. Modulo 2, how many 2's are there in 2? 1. What's the remainder? 0. Okay, so we've already seen another example of how this works. And so what's going to end up happening, I said we'll see modular products. What we're really going to be interested in when we get back to application is what we're going to call modular exponentiation. And so what this boils down to is we're going to want to calculate maybe something like 4 to the 16th mod 3, where now we had two numbers a to the b, modulo something. So can people believe that what's going to come in front here, that 4 to the 16th, might get really big really fast? Yeah. And in particular, just from the cryptography's perspective, picture that your computers in general, instead of having the number 4, you're going to have some integer that's 100 digits long. And instead of having the number 16, you're going to have some integer that's 100 digits long. Anybody willing to believe that a 100-digit integer raised to a 100-digit integer power is a really large number? Okay, you believe me. Good. And so the question is, how can we go about calculating that? Now, in principle, could we just calculate that exponent and then just do the modulo n operation? Sure, we could. Well, if you get a calculator to do that, you better have a really good calculator, because I'm going to be willing to guess the number that you get is going to be too big for most calculators to handle. And so one of the ideas is we don't actually have to calculate out that exponent if we want to do modular work with it. Okay? We don't need to know anything about 4 to the 16th to actually calculate 4 to the 16th mod 3. Because what we can do is think about breaking up this 4 to the 16th, and we can write that as 4 to the 8th times 4 to the 8th mod 3. Okay, so now we've reduced those numbers quite a bit because we've made that exponent quite a bit smaller. And we can use then our product rule, which I've rewritten here on this slide. So we know that 4 to the 8th times 4 to the 8th mod 3 is just equal to 4 to the 8th mod 3 times 4 to the 8th mod 3, all mod 3. And does that look like a simpler thing to work with? Yep. Well, maybe 4 to the 8th is still too big. So what would we do to 4 to the 8th? We could maybe break it up into 4 to the 4th times 4 to the 4th. Do this. Well, maybe 4 to the 4th is too big. Well, we could break it up into 4 squared times 4 squared. Okay, now we're getting at the region. Is anybody bothered by 4 squared? Does that seem like an unreasonably large number? No, I think 16 in a lot of cases is, we're good with 16? Okay. Seeing as I'm guessing all of you have at least that many orbits around the sun under your belt, we're good with 16. Just to say you're all at least 16 years old. Okay, and so then what's 4 to the 16th modulo, or sorry, what's 16 modulo 3? Okay, well how many 3's are there in 16? There are 5, and the remainder is 1. So we can calculate that pretty straightforwardly, and then sort of work our way back up then to 4 to the 16th. Okay, so maybe I'll let you work that one through on your own time, but what we'll do for an example is actually look at 13 to the 9th mod 7. Okay? So how does this work? Well, let's come back over. We'll start up a new slide here. And so what we're looking at calculating is 13 to the 9th mod 7. Anybody happen to know what 13 to the 9th is off the top of their head? Okay, this is something your calculator can actually do. This is a small enough number. It's a little over 1 billion, as I recall correctly. Somewhere about that range. So is that a big-ish number? Okay, for human beings, yeah. For a computer, no, not really. But for our example, works just fine. Do we necessarily want to take the time? Suppose you didn't have a calculator. Do you want to calculate 13 to the 9th? No, I don't either. It sounds awful. Okay, so what we can do is use that multiplication rule, and we can break this up. Now, is 9 divisible by 2? Not necessarily. So how might we want to break this up? What was that? Okay, so we could do 13 cubed as one of them, which would leave us 13 to the 6 as the other one. We could certainly do that. I would go a slightly different route. Anybody have an idea? Try to break up the two factors as evenly as possible, which is going to keep sort of both of the exponents as low as can be. Right, so what we can do is maybe break this up as 13 to the 5th times 13 to the 4th. And so we can have that mod 7. And using our multiplication rule that we just had, we can write this now as 13 to the 5th mod 7 times 13 to the 4th mod 7, all mod 7. Okay, so now do we have to actually calculate 13 to the 9th? Nope, now we have 13 to the 5th. Okay, that still sounds awful. Does anybody disagree with that? Okay, so let's think about that value for the moment. We'll have our 13 to the 5th mod 7. How can we think about going and doing this calculation? Right, well, we can break this up and say, well, this is just equal to 13 cubed times 13 squared mod 7. And again, we can use our modular arithmetic rule to say, well, this is just now 13 cubed mod 7 times 13 squared mod 7, and then with another mod 7 at the end. Okay, well, 13 cubed. Anybody know that off the top of their head? That's not one I know either. I know 13 squared. We'll come back to that point. But what do we do about the 13 cubed? Split it again until we get to something that's easy enough to work with. So we can now have our 13 cubed mod 7 is equal to maybe 13 squared. Everybody's comfortable just writing 13 to the 1st as 13? Okay. Mod 7. I know, I told you, this is going to be a really tedious calculation in a lot of cases. But I don't think conceptually there's anything really awkward going on. And so we now get this as 13 squared mod 7 times 13 mod 7 mod 7. Okay, so now I've got a whole bunch of algebra breaking this up. And have we actually computed anything yet? No. So let's go to a new slide and start doing that. So if we sort of look down to the bottom here, we notice that there's basically two things we need to compute at this moment. We've got a 13 mod 7 and a 13 squared mod 7. Do either of those seem particularly awful? Probably not. Okay, so let's go to a new slide, and let's do that. So we've got 13 mod 7. Okay, well, how many 7s are there in 13? 1, and what's the remainder? 6. Okay, well, that wasn't so bad. And we needed 13 squared mod 7. Well, what's 13 squared? It's 169. How many 7s are there in 169? Feel free to use a calculator. I think it's 24. Because 20 would be 140 and 24 would be 168. Which also makes sense because there's 168 hours in a week, which is 7 times 24. Okay, so what's the remainder? Just 1. Okay, well, that wasn't all that bad, maybe. So now we can come back and looking at our formula here for the 13 cubed mod 7, we get that that's 13 squared mod 7. Well, we saw that that's equal to 1 times 13 mod 7, well, that's equal to 6. And so what we end up getting now is 13 cubed mod 7 is equal to 1 times 6 mod 7. Well, what's 1 times 6? 6. And what's 6 mod 7? Just 6. Are there any 7s in 6? No, so we're done. Okay. Well, did that really turn out to be all that painful? Not really. Okay. So now let's come back to our slide. What was that?
No, I did it straight from 13 times 34, but I still got 6.
Yep. Okay, so what we now know, we can start putting in here, this was 6, this was 1, and we got that this was 6. Okay, well, so now let's look at our 13 to the 5th. Do we know 13 squared mod 7? Yeah, we've already calculated that. That's just 1. And do we know 13 cubed mod 7? Yep, we already calculated that. That's just 6. That's what we just did. Okay, so 13 to the 5th is now equal to 6 times 1 mod 7. Well, 6 times 1 is 6, which mod 7 is 6. Okay, so we can get that without too much effort. Okay, so now coming back up to our original problem of the 13 to the 9th, okay, well, we've got 13 to the 5th mod 7. Do we know that? Yep. That's 6. Do we know 13 to the 4th? Not yet. We haven't actually calculated that one. So let's take one more slight digression and go do that. So we can get 13 to the 4th mod 7. Does anybody know 13 to the 4th off the top of their head? Good. Neither do I. Okay, so what we can do is write this as 13 squared times 13 squared mod 7, breaking it up, and take this out, so we get 13 squared mod 7 times 13 squared mod 7. And do we know 13 squared mod 7? I have up above that it's equal to 1. So this is now equal to 1 times 1 mod 7. Well, what's 1 times 1? 1. And what's 1 mod 7? 1. Okay. So when we come back to our previous slide, that's just a 1. What's 6 times 1? 6. And what's 6 mod 7? 6. Okay. So we ultimately get at the end of all of that 13 to the 9th mod 7 is just 6. Did we ever have to really think about a particularly large number? No, we didn't. Okay? And I think that's kind of cool. And so again, when we start getting into the actual cryptography, and we look at how Diffie-Hellman works, and we get into what the RSA algorithm, and we'll get to that certainly next time, we're going to start to see that we're going to need large numbers to large exponents to make this work. But the beautiful thing is we don't ever have to calculate what that number actually is. We can use these types of rules because we're always going to be interested into some number to the some number power modulo some amount. Okay? And that's what's going to make this happen, because what this is telling you is that computers can actually do this. First of all, they can do it in a reasonable amount of memory, and they can do it reasonably quickly. Okay? Are both of those things important when we want to develop something that's usable? Yeah. Okay. Any questions on this example? Okay. Hopefully, hey, look, the answer's even 6. Good, we did it right. Okay. And so we get our answer is 6, and there's that. So, as we've already said, so why are we bothering with all this modular arithmetic? As I've said, it's going to be key to RSA and to Diffie-Hellman. As I've already said, modular arithmetic keeps the numbers relatively small. So from that last example, I said it was 1 billion. Excuse me, it was about 10.5 billion. 13 to the 9th is 10,604,499,373. I know you're all thinking that. But the 13 to the 9th mod 7 is just 6. Okay? So this tells us, again, computers can store these numbers with just modest space. We don't need huge amounts of memory to work with them. And then, as we said, we're going to need to see some very large numbers when using the RSA or Diffie-Hellman. But if we only need the large number modulo some other amount, it's not going to be so bad. Okay? So that's why we're working with this sort of just thinking ahead a little bit. We'll get back to all of these points on Wednesday. We're also going to need, though, some elements of number theory. And so I just want to introduce these. And so one thing that we'll need, again, probably thinking back to elementary and middle school, we're going to need the greatest common divisor of two numbers. And so what that says is we have two numbers, a and b, and we're looking for the largest integer that divides both of them. Okay, so for a couple examples, what's the greatest common divisor, or GCD, of 4 and 6? It's 2. Is 4 divisible by 2? Yes. Is 6 divisible by 2? Yes. Is 4 divisible by any other numbers? Well, okay, 1, forget 1. It's not really that important. But it's divisible by 4. Is 6 divisible by 4? No. Well, it's not completely. No, it isn't. Okay. And so we know then 4 can't be the GCD because it doesn't divide 6. But 2 is. Okay. So we get a GCD of 2. What about for number 2? What's the GCD of 5 and 25? It's just 5. Because does 5 divide itself? Always. And does 5 divide 25? Yep. Okay, and so we can do that. And the way that the GCD is often written is in this way here of saying GCD and then sort of in parentheses, what are our numbers A and B? Okay, so now in the limit that we've got sort of these really small numbers here, is this really that hard to work out? Not terribly. But maybe we're going to want to use larger numbers at some point. And so one way that we can think about trying to calculate greatest common divisors is to use something called Euclid's algorithm, which is one of the oldest known mathematical algorithms. This was originally reported by Euclid. Does anybody know when Euclid lived? Sometime around the 400 to 300 BC. So this is actually not really modern, but yet still actively used. Okay? And so what we can end up doing, in the way this algorithm works, is we'll say that if we want to know our greatest common divisor of two numbers a and b, that's going to be equivalent to the greatest common divisor of b and a mod b. Okay, so whatever our values a and b are, if we don't know that greatest common divisor by simple inspection, it's a little bit too complicated, we can flip this around. Okay, so b sort of stays the same, but a mod b, what's the biggest value a mod b can have? It'd be b minus 1. Okay? And so we can now think about making these numbers smaller and smaller and smaller as we iteratively or recursively do this, to the point that ultimately something looks trivial. Okay? And so typically what will happen is, as a convenient base case, is we can write that the greatest common divisor of a and 0 is a. Again, is that really a true statement? No, because does anything really divide 0? No, but we'll use sort of a notational shorthand to sort of be, this is the end of the algorithm. Okay? And so what we can do is start to use this is to find the greatest common divisor of 96 and 142. Again, maybe in a computer's mind, these are not particularly large numbers, but to us as humans, is it immediately obvious to any of you what the greatest common divisor of 96 and 142 is? No, and it's not to me either. So we can start to look at that. So we'll pop back over here. And so we want to know greatest common divisor of 96 and 142. Okay, so I know the formula is not up on the board. I apologize that I can't have this and the slides on in a way that makes them readable. But what we can do is we can say, using this Euclid's algorithm, that this is equal to GCD. And the way it works is you flip the order. So we can pull our 142 down here, and we'll have 96 mod 142. So again, this is now 96 is A, coming down here. If 142 was B, so we get a B and a mod B. And so there's our way of saying GCD of A and B was equal to the greatest common divisor of B and A mod B. Okay, just sort of flip those two numbers around. Okay, well, we can continue along with this. And we get, this is now the GCD of 142. And what's 96 mod 142? Well, how many 142s are there in 96? 0, so it's just 96. Okay, so far, have we actually done anything? Does it surprise or bother anyone that the greatest common divisor of 96 and 142 happens to be the greatest common divisor of 142 and 96? No, we haven't actually said anything so far. Great, so we're off to a good start. Now's where the magic starts happening. So we can apply Euclid's algorithm again. swap the order, so we get the 96 coming in front, and then our A, 142, mod B. So now we get a 142 modulo 96. What is that value going to be equal to? I get 46 in my head. Okay? So now what we know is that this is now equal to the greatest common divisor of 96 and 46. Notice we've now made that 142 go away, and it's been replaced by a significantly smaller number. Okay, now we're starting to make some progress. Okay? So we can apply, or I guess I should ask at this point, is it obvious to anyone the greatest common divisor of 96 and 46? No. So we can apply Euclid's algorithm again, switch the order, so we'll get a 46 and a 96 mod 46. And what's 96 modulo 46? Can 50 be something modulo 46? It's just 4, right? Because there are two 46s in 96. I get 46 times 2 is 92. Okay? So we now get a GCD of 46 and 4. Okay, well now we're getting something that's starting to look manageable. Are we good with 4? Okay. We probably could figure this out without a lot of effort at this point, but let's just continue iterating here. Using Euclid's algorithm, again, we get that this is the GCD, 4 and 46 mod 4. Well, how many 4s are there in 46? 11. And so we get a remainder of 2. And so this is now the greatest common divisor of 4 and 2, and is this now sufficiently trivial that we can sort of inspect it and get the result? Yeah. What's the greatest common divisor of 4 and 2? It's just 2. And so we can start with these sort of largish looking numbers where we don't have really a good feel for what the GCD was of 96 and 142, but by using this Euclid's algorithm, we can go through it sort of step by step and ultimately get something that's not that bad to work with and see that we get 2. Okay. So we've got the 96 and 142 is 2. We can also do the same thing for 117 and 6. Do people want to see that worked? Or do you want to work it on your own time and I'll give you the answer and you can check yourself against it? Okay, we'll do that. So sure enough, for 96 and 142, our GCD was 2. And if you want to go check on your own time, the greatest common divisor of 117 and 6 is just equal to 3. Question? If you plug in 2 prime numbers, will you end up with 1? Yes. And what a wonderful, wonderful segue. Because the next thing we need to talk about are prime numbers. Okay. So an integer is prime if the only integers that divide it are 1 and itself. Okay. So, for instance, is 2 a prime number? Yes, because it's only divisible by 1 and 2. Is 3 a prime number? Yes. Is 4 a prime number? No, because it's divisible by 2 in addition to 1 and 4. So how many even prime numbers are there? Exactly 1. It's 2. Any other odd number has to be prime. Okay? And so one of the things that we'll see is that then prime numbers cannot be written as products of other integers. So the only way you could write it as a product would be to say, like if we've got 7, 7 is equal to 7 times 1. You can't have any other integers in that product and still get 7 because it's prime. I'll just put the note here because someone usually asks a question about it if I don't. 1 is debatably prime. There's not necessarily consensus as to whether it is or isn't. What there is consensus is that no one usually cares. Okay? And just as a note, prime numbers turn out to be very central to number theory. If you're interested in sort of what's going on here in all this modulo arithmetic, a class on number theory will be right up your alley. Okay? And there's certainly more information on prime numbers if you want to take a look on Math World there. And so one of the reasons why prime numbers are going to be important is they allow us to do one thing called prime factorization. Oh, question?
What was the opposite of prime? I forgot the word.
So I think if it's not prime, it's the composite, I think is what it's called. Okay? And so the reason one of the reasons we're going to be interested in prime numbers is we can take every integer and uniquely write it as a product of prime numbers. So for instance, we can take 12 and write that, okay, so we know 12 is equal to 4 times 3. Well, 3 is prime, 4 isn't, but 4 can be written as 2 times 2. And so we can ultimately write 12 as 2 times 2 times 3, a product of prime numbers. And if you're so inclined, you could combine the 2's and say it's 2 squared times 3, indicating there's 2 factors of 2 in that number. This is going to turn out to be fairly useful later. What ends up happening, I'll just give you the foreshadow, the computers, when we start getting into these algorithms, are going to share the number 12. And the really expensive thing that Eve would have to do if she wants to crack our ciphers and crack our security is to factor 12 into all of its prime numbers. If Eve were able to do that, all of the cryptography we're about to discuss in the next couple of days, gone. And in principle, there's nothing stopping Eve from doing it. There are well-known algorithms for how to do it, but they are expensive. As the numbers get large, and I guarantee you the numbers we're using in cryptography, we're not going to give you something as small as 12. Think of this as now probably being a number that's like 300 digits long. Okay? Very expensive to do this operation, which is what makes the cryptography work. Okay, so then maybe as our last example today, we can determine the prime factorization of 29,400. Okay? Anybody have a guess as to what that is? Good. Okay, so we're going to back out and go over to the whiteboard again. And so we had 29,400. And so we want to find the prime factorization. So usually in my mind, the easiest place to start is to just start at the bottom of the prime numbers and start looking at how many factors we have. Is 29,400 divisible by 2? Yes, it is. Okay, so we can factor out a 2. And what we have left is 14,700. Okay, so we can now repeat the same thing. Is 14,700 divisible by 2? Yes, it is. Okay, so we now have a 2 squared. And what's left when we pull out that next factor of 2? Yep, I get 7,350. Is that divisible by 2? Yes, it is. So we get a 2 cubed, and what's left? I get 3675. Okay. Is 3675 divisible by 2? No. So are there any more 2's for us to pull out? Nope. So we go to the next prime number. And what's the next prime number after 3? After 2? It's 3. Okay. Is 3675 divisible by 3? Yes, it is. Okay, so we can pull out a factor of 3. So we'll have our 2 cubed times 3. And what do we get left if we pull that 3 out? We get 1225. Okay, so we can then ask ourselves, is 1225 divisible by 3? And it turns out it's not. Okay, so are there any more factors of 3 to pull out? Nope. What's our next prime number? 5. Is 1225 divisible by 5? Yep. So we have now our 2 cubed times 3 times 5. And what's 1225 divided by 5? I get 245. Okay? And so now, likewise, we ask ourselves, is 245 divisible by 5? Yes, it is. So we have now a 2 cubed times 3 times 5 squared. And what do we have left at that point? 49. Is 49 divisible by 5? Nope. So we go to our next prime number, which is 7, and trivially 49 is equal to 7 squared. So we can now put this as 2 cubed times 3 times 5 squared times 7 squared. And so that is our prime factorization of 29,400. We know that there are three factors of 2, 1 factor of 3, 2 factors of 5, and 2 factors of 7. That's probably a good place to end for the day, so thank you for your attention. Remember, your homework is due tomorrow morning, and I will see you on Wednesday.